Okay, thank you for coming to this seminar, and thanks very much for the invitations to all the links fellow, especially to Professor Bacheli and Dr. Noiri for the invitation. I am Avhishek Chatterjee. I am an assistant professor in Indian Institute of Technology, Madras, or in short, we call it IIT Madras. So IIT Madras is one of the IITs in India that you might have heard of. It's the flagship institutes in India, and it's one of the oldest IITs also. It was started in 1950s, and currently IIT Madras is ranked one in the Indian government ranking, the National Institute Ranking Forum. So I am in the electrical engineering department. So by training, I am an engineer. So I did my PhD from University of Texas in Austin uh, in the ECE department with Professor Francois Bacheli and Professor Sriram Vishwanath, I work mostly with them. Then I did a postdoc at University of Illinois Urbana-Champaign, and then I joined IIT Madras around 5 years back. So my main interest is actually in networks. So I work in broadly my area will be stochastic networks. So where I work on communication networks and also social networks and crowdsourcing systems, which also fall under the broad category of stochastic networks. And my recent interest is in quantum networks, so quantum communication networks, and also quantum computation, where you can think of the quantum circuits or also as networks. So in this talk, actually, I'll try to talk about that. How can, hello, is there a question?
No
So I'll
problem.
talk about, okay. I'll talk about a result about quantum computation, in especially fault-tolerant quantum computation, or you can say it's a converse kind of result. So what it says is, in the presence of the noise, quantum computers have certain limitations, and we are trying to investigate those limitations. So this talk will do that. But the main thing is that we try to connect this quantum computation problem with quantum communication problem, and we'll try to use quantum Shannon theory to get the converse. But I won't be able to get into all the details because, as I had mentioned in my abstract, that I won't assume that a background in quantum communication or quantum computation. So I'll start from zero. So that's why I a priori apologize to the experts like Dr. Noiri, because there will be some redundant stuff, and I may not be able to get into too much of the technical details. But nevertheless, I think there will be something interesting for everybody in this talk. Okay. So without any further delay, I'll start the talk. So this is a joint work with my PhD student Uttara Kalyani at IIT Madras and Anuj Nayak, who is a PhD student in University of Illinois Urbana-Champaign. Okay. So I'll start my talk with just one slide summary first, that what is I am going to talk about, what is the result, so that we have a perspective. Going forward, we'll get into some details, so we can keep this summary in mind. Okay. So first, we all know that quantum computers, people talk wonderful things about quantum computer. One of the main things is that they can solve certain problems faster than classical computers. For example, factoring, where no good classical algorithm is known, but there is quantum algorithm. Okay. So theoretically, they're very good. But what happens in practice, there are certain issues. For example, quantum circuits, unlike classical circuits, suffer from noise. The technical term for this is decoherence or gate failure. And that can actually derail the computation. And it actually can result in a very erroneous computation if the noise is not handled carefully. So the noise has to be handled carefully. So two ways of reducing noise. One is coming up with better and better technologies where noise is lower and lower. But so far we have not been able to do that. Another promising approach is something called fault tolerance. So come up with algorithms or computational schemes which will work even in the presence of noise. Okay. So one of the main approach in coming up with good quantum computational algorithms is coming up achieving good quantum fault tolerance. So what does it mean? It means reliable computation on a quantum computer is possible even if the noise is below a certain threshold. So what quantum fault tolerance guarantees, the main quantum fault tolerance theorems that guarantees that reliable quantum computation is possible if the noise is not too high, below a certain threshold. Then the noise can be eliminated out of the system. So the way it's done generally in a broad sense, like in a very, very high level sense, is that computation is done on something called qubits. So in classical world, the computation is done on bits. In quantum world, computations are done on qubits, or in it's a short form for quantum bits. So the computation is done on something called logical qubits, which are the function of certain. So the logical qubits are the mathematical objects, those with which we have to do the computation. So each of this logical qubit is actually realized using real physical qubits, which are like physical quantities. But physical quantities are noisy. So what they do for each logical qubit, they kind of take multiple noisy physical qubits to uh, realize, to kind of create that logical qubit. And the idea is, by doing so, we can kind of accurately, not in a true accurate sense, but more or less accurately mimic the logical qubit using multiple noisy physical qubits. So one way of looking at it would be like, look at communication scenario. What we do in communication, if the channel is noisy, you use a code. One of the simplest code is a repetition code. Like for each bit one or a bit one, we repeat it few times, say 5 times, and then do a majority decoding. Okay. So this is similar to that, but with the main difference in quantum, this repetition or this copying is not allowed. So you have to do something clever. Okay. But this can be done, and that is how fault tolerance is achieved. And there are many interesting error correcting codes which achieve this. Just like in the classical world, there are interesting error correcting codes to like LDPC codes and polar codes and other things. In quantum world also there are very interesting codes. Okay, but we won't get into those details because the goal of this talk is to understand the converse. What is a converse? Just like in communication, there is a Shannon capacity achievability scheme, the coding schemes that achieve certain rate, and there is a converse that you cannot go beyond that rate. In quantum fault tolerance, the converse is of this form. That, as I said, to realize one logical qubit, you need certain multiple noisy physical qubit. They are kind of guarding that logical qubit. So the question you may ask, how many such physical qubits do I need to kind of accurately realize the quantum computation? So that ratio of number of physical qubit to logical qubit, which will be always more than one, is called redundancy in the system. And we want to have a lower bound on redundancy. Like what is the minimum redundancy do we need in the system to achieve fault tolerant quantum computation? And there is another aspect to the converse result also. For example, note here I said that in quantum computers, fault tolerant schemes can achieve almost reliable computation if noise is below a threshold. So one may ask the opposite question: what is the noise threshold? So that if the noise is more than that, then there cannot be any quantum computational scheme which will do reliable computation. So it's just the opposite. So achievability versus converse. And in this talk, we'll be interested in this converse part. Okay. And you may ask, why is it important? It's important in the same sense as a converse for a channel capacity in Shannon theory. Like it's good to know what's the limit so that when you're close to it, we know this is a point to stop. Okay. But there are certain other benefits also, which I'll discuss when I go there. Okay. Particularly in our converse. Okay. So in this talk, what I'll show you, so there are certain converse which exist already in literature. I'll do a recap of that. And at the end, I'll give you one more converse, which is tighter than the existing converse in terms of both lower bound on redundancy and the noise threshold, like getting an upper bound on the noise threshold. And the main interesting thing is that to get this converse, we connect the computation problem to finite block length communication problem. So you all know about finite block length classical communication problem like Polyansky and Verdu kind of paper. Here we connect this computation problem with a finite block length quantum communication problem or quantum information theory problem. Okay. So this is one page summary. Now I'll get into little bit details. I have to tell you what is the quantum computation model and what do I mean by noise in a quantum computation model and how this quantum computation model is different from classical. Okay.
Can I ask
So,
a question,
yeah,
Abhishek?
please,
Yeah.
Professor. Yes.
So, what is the analog of block length in this vision?
Yes. So here the analog of block length is the number of, so when you're doing computation in classical, you compute with certain number of bits. Say maybe it's a 64-bit computer, 256-bit computer. Here also in quantum, there is certain number of qubits you want to compute with. Currently it's 50 or 100, 50 between 50 to 100. So the finite block length means that so most of these converse results are what have been done in past. Therefore, the number of qubits I'm computing with going to infinity. What we do here, we give a bound with a finite number of qubits, uh, and that's why you have to connect with finite block length quantum information theory. And this finite number is the number of qubits I'm computing with. And this is generally roughly in the modern technology, something called Niskera. It's between 50 to 100.
Thank you.
Does that answer your question, Professor?
It does. Thank you.
Okay, thank you. So I'll go ahead. So we all know about the classical computation model, which is this one that I give to a classical computer. The input is a bit stream 0, 1. So there are n bits, which is an input, and I have to compute a function. And the output is some m bit. Okay, so n and m may or may not match. For example, if f is a full adder, then n will be 2m or 2m plus 1. Okay. In quantum, analogously, there is something called so in classical we have bit, in quantum we have qubit. Okay. So first let's understand what a qubit is. So in classical, a bit is 1 0. It's coming from a Galois field. Okay. In quantum, a qubit or a single qubit, which are denoted by rho 1, is actually one way of looking at it. It's just a complex number. Okay. It's sorry, not a complex, it's a complex matrix, C2 cross 2. So it's a complex matrix of size 2. So it's a square complex matrix of size 2. And it has to satisfy certain conditions, like it should be Hermitian, it should be positive definite, and its trace should be 1. So this is how a qubit is defined mathematically. Physically, again, I am not a physicist. So in this talk, we'll stick to the mathematical idea of a qubit. But physically, a qubit may be a spin of a particular particle, up or down. Okay, or a super or something called a combination of these two spins. They can all be related using this mathematical formalism, like it's a complex matrix, 2 cross 2. One qubit is a 2 cross 2 complex matrix which satisfies this property. Now, when it comes to n qubits, just like here in classical we had n, here also you can have n qubits. N qubits is another complex matrix which is of size 2 power n. Okay, so it's a matrix, square matrix of size 2 power n, but it should also be Hermitian, positive, and trace 1. So rho power n should also satisfy this property. One example, one simple example of this rho power n, or rho n, so this is what we call this rho n is a state of n qubits. So rho 1 is a state or a quantum state of 1 qubit. Rho n is a state of n qubits, a joint state of n qubits. One simple example of such a state is something called product state. So product of single qubit states. Okay, so that means those qubits are not kind of coupled in some sense. So you can, one analogy to the classical world, you can think of these are like some kind of a distribution. So they're like product distributions. Okay, so they're not coupled. But in general, they can be coupled. Okay, so rho n does not have to be always product. In quantum computation,
just a comment for some people. I already presented sometimes things about qubits. In fact, there are two ways for the qubit representation. The first one is the Hilbert space with vectors, but then you do not have you just have pure states. You do not have mixture of states with adding probabilistic mixture of different states. And this formalism is what we call the density operators. which is a way to represent, which is more powerful in some ways, which is a way to represent the not only pure states but a statistical mixture of quantum states. Just to add something, all what you did, what you say is correct, but in terms of background, this may be disturbing for some people having this representation with density operators.
Yes. So this Dr. Noiri, whatever he said is perfectly correct. So what I'm going to the most general formulation. So there is another formulation where you can think of states live in a Hilbert space. That will, there you can only capture, as he said, pure states, but we are interested in what is called as mixture of states. And there this formalism helps, like where you can think of these things as matrices, or more generally an operator from all Hilbert space to the same. So they are the equivalent. One can show that the Hilbert space formulation can be presented by this one. So they're equivalent. So in all senses. Okay. Yeah. Thanks for the comment. And so a quantum computation operation is generally given by, I am giving an input to the quantum computer, and it's being operated by this unitary matrix, which is of the size again 2 power n, the square unitary matrix. So it's like, so the output of this quantum computer circuit will be u rho n. So dot will be rho n u dagger. U dagger is the adjoint, the standard adjoint of a complex matrix. And there will be an output sigma n, which will also be this complex matrix into power n cross 2 power n. Okay. So this is how the quantum structure, quantum computer circuit generally look like when a quantum input and quantum output. Okay. There are some more differences. So first of all, in the classical world, when I want to realize this function f or Boolean function f, the way we do it is there will be some gates inside, Boolean gates. So all of these gates will have input g, like g number of inputs, that g may be 2, 3, 4, 5, depending on the particular technology, what we generally call the fan-in of the gate, and we'll have one output. Okay, and they will only allow Boolean operations like AND, OR, NAND, NOR. Mostly there are certain universal Boolean operations using which you can do anything. And one important thing to note here is that this output can be copied, in the sense of, for example, in this case, there is output of a gate which can go to two different gates. And why I'm mentioning this is obvious in classical, but in quantum, this is not allowed. So let me talk about the quantum gate in this context. So what happens, the quantum circuits are also realized using quantum gates. So the quantum computation is also realized using quantum gates, which have G inputs and G outputs. Here, the number of inputs and number of outputs are same, okay, unlike the classical case. And each gate can do only unitary operations, okay, which is because these are all matrices and you can do this U dagger operation. And as a result, the whole circuit and also can only do U dagger operations. But there are some catch to it. I'll come to that about the whole circuit. But each gate can do only these unitary operations. And copying is not allowed. So you cannot copy one qubit and create two qubits. There's something called no cloning theorem, which forbids this. Okay. And another important thing here is in classical, if you have one bit, you can observe it. You can say what that bit is. You can take a look at it and probe it. In quantum, every time you probe something, you disturb the state. So probing is not obvious like classical. So there is this probing is called observation or measurement, which is interesting in its own right, but I won't get into the details just in the interest of time, and it's not won't be so it won't be a roadblock for understanding the results that I'm going to present forward. Okay. So this is the this is the quantum computation model. Okay. Now one may ask, what is the use of this model? The use of this model is that suppose you want to solve a hard classical problem, say factoring, okay, which is known to be hard. What it will do, you'll take the classical input, say a number which you want to factor, put it in its binary representation, then you have to map the classical input to a nice quantum state like this one. And then there will be a quantum circuit where you run a clever algorithm, okay, and get a quantum output. And at the end of it, from the quantum output, you have to back it to a classical output. This mapping is generally done through something called measurements, which you won't get into the details. And you will get the final output, classical output, and the factoring will be done, and will be amazed to see the factoring will be much faster than what can be done in classical. For example, in classical world, no polynomial time algorithm is known, but in the quantum, if you do this quantum part cleverly and do the mapping from classical input to quantum input cleverly, the factoring can be done in using polynomial number of computations. Okay. But we won't focus on the classical input and the classical output. That's why I'm not getting into the measurement part. We'll only focus on quantum input and quantum output. We'll only focus on quantum circuits which have quantum input and quantum output. The reason is simple. The first reason is that there is something called quantum Fourier transform, which is used in many classical algorithms, including factoring that I said. Also, there is something called discrete log. Then there is something called subgroup problem. In many of these problems, a common quantum circuit engine is used, which is quantum input, quantum output. This is called quantum Fourier transform. And this is a versatile engine and used in many problems. So it's worth kind of investigating this versatile engine itself, how good it is. Okay. And said that that's from the point of view of an engineering application. Okay, so it's a versatile engine for many engineering problems. But there is another aspect to it which is very scientific, is that if you want to kind of numerically emulate a physical and chemical process, quantum computation or quantum circuits is a way to go. So quantum input, quantum output, quantum circuits. So quantum circuits which have quantum states as input and quantum states as output is a way to simulate or emulate new physical and chemical processes. Why are they of interest? They are of interest first of all for pure scientific purpose, because you want to understand certain systems whose experiments are not easy to do. But there are a lot of applications also, because the quantum chemistry or chemical processes have applications in drug discovery, cancer treatment, many applications, again, which I am not an expert about, so I won't talk much. But main thing I want to focus on, that our interest is in this part. We give a quantum input and we get a quantum output, and want to understand how accurately we can do that. And if there is a noise in the circuit, how this process is being affected. Okay, so that's what we want to understand.
Avhishek, can I ask a question?
Yes. Sure, please.
Naive question, I'm not expert at all, but so you alluded to transforming non-polynomial problems into polynomial ones. So I understand that thanks to the 2 to the n, you move from, I mean, you can move to the exponential very efficiently, but it is provided that this multiplication by this unitary things is done in time which is linear in n. So I don't understand, just based on first principles, what is the reasoning which allows one to say that you can transform something which would be exponential in complexity in the real world into something which is exponential in this world? Could you explain that?
So this intuitively what I can say, so mathematically it's not proved nowhere that quantum models are actually faster than classical. So for example, if that's done, then P equal to NP or those things will have some issues. What is only known so far is that certain classical problems for which we do not know of a classical algorithm as of now, like good classical algorithm. That does not mean there does not exist a classical algorithm. We just have not found them yet. But luckily in the quantum model, there is a very fast algorithm. So that does not mean that actually this does not prove mathematically that quantum computers are more powerful than classical computers. What we only know that for certain problems, classical problems, quantum computers gives faster solution. On the other hand, for those problems in the classical computer, no fast algorithm is known as of now. But it may happen after 20 years, somebody will find one. And nobody has proved that quantum computers are strictly more powerful than classical computers. Nothing like that has been proved. This is only very problem specific. Intuitively, what I will say that problems that have some kind of a periodic structure, quantum can solve them faster, and mostly by use of this quantum Fourier transform kind of technique. But that does not mean quantum computer will be powerful in all problems compared to classical problems.
Thank you.
Maybe I can complement with the example of factorization of numbers, of integers. The faster classical algorithms are not polynomial. They are sub-exponential, but not polynomial. With the Shor algorithms, it is a polynomial in n. I do not remember exactly, maybe n square root of n, or it's very, very shorter time. But this doesn't mean that we do not know today if maybe there exist some algorithms that can factorize integers in a polynomial time, classical, but we don't know them if they exist.
As an extra compliment, I believe there have been advances recently showing that, well, suggesting that if we can do really quicker if we can show that we can do things faster with quantum computers and classical computers, then we have something that tends to suggest it proves that P is different from NP. We have bricks that go in that direction, not a whole proof. So it's sort of in that awkward space where we probably won't be able to tell for a very long time.
Thank you.
Okay. Yeah, thank you. So yes. So there's okay.
So,
shall I move?
Yeah.
Okay, thank you. So okay, so okay, so now, as I said, so this we'll focus on this quantum input, quantum output circuit, and particularly want to understand what is the effect of noise. So, for example, and for that I have to first say what is the noise and how is it modeled and what is its effect. Okay, so let me talk about noise in quantum circuits, noise and decoherence of qubits. So as I said, in quantum world, like classical world, there is this in quantum world there is this qubits which are quantum states. Uh, but unfortunately, these physical quantum states sometimes go through a process called decoherence because of its interaction with the whole environment around it. Unlike physical classical bits, which are very stable because they're stored as a voltage in some CMOS or something, qubits are not that stable. They undergo decoherence, okay, and lose information. So the qubits kind of decohere into some kind of a random state. And not only that, the quantum gates can also fail because they are quantum operations, they can also fail. And that leads to some kind of an error. Okay. So for example, so suppose if this gate, while a qubit going to this gate undergoes noise or decoherence, and also this gate fails, then the output of this gate, these qubits will be erroneous. It won't be what I expect it to be. And as a result, the final output will also be erroneous. Okay. So next, the first thing to then understand how do I model this effect of decoherence and gate failure? So one very interesting way of modeling it, which has been proved to be quite effective, is that think of a qubit being processed by a gate, a correct gate. And so suppose if everything was perfect, there is no noise, there is no gate failure, then you will get some output, which is the noiseless or desired output. But you get some actual output, which is a noisy version. So think of this noiseless and desired output being passed through a noisy quantum channel, and that's actually is your actual output. So your actual output is the noiseless or desired output if there is no gate failure, no decoherence, passed through something called a noisy quantum channel. So that has been a very good mathematical model for this kind of decoherence and noise. So now then I have to first we have to understand what is a noisy quantum channel. So it has similarity to classical channel or noisy classical channel. So I'll go through one example, which is the most popular model for noise in many of these problems. Is called depolarizing channel. So what it means is that suppose I have a k qubit state rho k, which lives in this matrix of C2 power k cross 2 power k. A depolarizing noise is of this form. So if a noise generally in quantum channel model is an operator on this state rho k, which is a matrix. So the output of this will be a mixture of rho k, which was the original. So 1 minus p, where p is a number between 0 and 1. 1 minus p times this plus p times this is an identity matrix. This I in of size 2 power k, 2 power k. But I have to normalize it by 1 by 2 power k, because I have to make sure that this matrix has trace 1, because that's a kind of a requirement for my quantum states. Okay, so this is kind of one of the.
Sorry, Avhishek, just to comment on this. In fact, this is where we see that it is a mixture. In fact, you have a probability 1 minus p having one pure state.
Yes.
The pure
Yes,
state, for example,
yes.
and then the other is a purely random qubit or n qubit system.
Yes, true. This is another way of looking at it, and I was going to mention it because this way, another way of looking at it helps. Okay, but note that you can interpret this as Dr. Noyeri has mentioned, that you can interpret as a kind of a mixture, in the sense that with probability 1 minus p you get what you wanted, rho k, but with probability p you get a totally random state, and this I 2 power k 1 by 2 power k is actually the totally random state whose entropy is maximum. So in classical analogy, this state is like my uniform distribution, which has entropy 1. So what we see is with probability 1 minus p, the real state, and with probability p, the totally entropic state. Okay. So okay, we can ignore this part, this equation. This is one of formal way of writing noise using a unitary operator, but this is not so important for this talk. What is important, another thing that I want to say, that note that this noise operator is working on a k qubit state, because rho k is a state of k qubits. Similarly, for k equal to 1, it will be operator on 1 qubit. So if I put k equal to 1 everywhere, then for 1 qubit, this would be the depolarizing noise for 1 qubit. So what happens that when k qubits are together, the noise can operate on them independently, depending on the particular physical scenario, or can work on them jointly. But what is believed in many practical settings, this independent acting of in qubit, so the noise acting on each qubit independently, is often thought as a good assumption. Okay. So when this noise is i.i.d. across qubit, for each qubit it operates i.i.d. This nk is written by this notation, and this is called the tensor product. What it simply means is that these n1, which are 1 qubit noise, are operating in a tensor product sense on the state. So the analogy with the classical will be, in classical we know that when the noise is i.i.d, the output condition on the input factorizes into product form. So this is also that product form. Only in quantum, the product form is this tensor products. Okay. So this analogy is also very helpful. Okay. And we'll be mostly studying this kind of independent noise, because that's what mostly studied. But said that there are cases where you may say non-independent noise. Okay. So to take away from this is, noisy quantum channel is actually, one way of looking at it is actually it's a deterministic operator, because this operation is deterministic, but it's some sense irreversible. Irreversible, by that I don't mean it's non-invertible. It's invertible. It's an invertible operator in mathematical sense, because if you know nk rho k, and if you know p, you can get back rho k. But it's irreversible in the sense that in quantum computation, only operations that you're allowed to do is these unitary operations. By doing those unitary operations and something like measurements and other things, you cannot go back from nk rho k to rho k. So though this is like a deterministic operation, but you cannot negate the noise and get back the original thing. But said that, as Dr. Noiri was mentioning, this probabilistic interpretation of depolarizing noise is very helpful. It's like you can think of that with probability 1 minus p, I am getting the correct state. With probability p, I am getting a totally noisy state. Okay. So that's, I think, for this talk, that interpretation will be more than sufficient. Okay. Is there any question so far? Because before I go ahead, I want to, if there is any questions, I would like to answer first, especially if any clarification questions.
No questions.
Okay, thank you. So how am I doing on time, Professor?
You have 20 minutes left.
20 minutes left. Okay, good. Okay. So now let's try to understand how does this noise model help us to understand the noisy computation model. So first, forget about noise in the computation model. So if there is no noise in the computation model, what it would be, there will be an input state and there will be these gates. The gates will be operating on different qubits. Then there will be another set of gates will be operating on the output from the previous gates and so on. So the operation will happen in layers. I call them O1, O2, OL and so on. And finally you get an output. So if there is no noise, you will get whatever you desire to get. Okay. But because there is noise, after each of these gate, what we'll see, as I said, actual output of a quantum gate is the noiseless desired output passed through a quantum channel. So we understood what a quantum channel is. So what will happen mathematically, after each gate, we'll see this noisy quantum channel. And as the noise works independently on each bit, I'll see this product form. So note that each gate has G input and G output. On each of them, noise is working independently. So after each gate, I have this noisy quantum channel. So my circuit will look like this now in presence of noise. Clearly, because of this noise, I won't get what I desire. I'll get something erroneous state, and depending on the strength of the noise, that state might be very far from what I desire. So in fault tolerance, the goal is to get what I want close to what I want. So what I want is, I want to do something with the circuit clever so that the output, this QC rho n, is very close to what I actually desired, that U rho n U dagger. That was the true thing I desired, and I'm getting this. I want them to be close. One way of doing it is the fault tolerance approach is, actually there are three main ideas. The first idea is to introduce something called redundant qubits. Okay, as I said, each logical qubit realized using multiple physical qubits. That's redundancy. Okay, another name for that is ancilla. Okay, there is another approach. There's something called encoded gate. That for each gate you use multiple gates in a fashion such that if one of them fails, still I can get the correct output. Okay. So that's another, that's called redundancy in gates. So you can have redundancy in qubits, redundancy in gates, we can add more gates. And there is another thing which is not so used so much, but you can use potentially, is the architecture. For computing a particular function or particular computation, there can be multiple architectures. One of them will be more robust to noise than the others. So one can try these three things: redundancy in qubits, redundancy in gates, and architecture. And the goal is the following. Goal is to make sure that this true output, remember this was our true output that we desired, and we are getting this. I want to make sure the distance between these two is less than some epsilon, some specified epsilon for all such good nice inputs. Okay. So this is the goal of fault tolerant quantum computing. Okay. And this distance, I won't get into the details of this distance, but there are many distances, something called trace distance, fidelity. In our paper, we focused on fidelity, but what is known, this fidelity and trace distance, they're equivalent. Okay, so you can deal with one of these. But again, the fidelity is not like a distance that in a true sense, but it's one of the good measures for closeness of two states. Okay. So as I said, the way to achieve this is using redundant bits and gates and redundant gates and modify the architecture. So there are some well-known fault tolerance schemes a very well-known fault-tolerant scheme, which is known as the concatenated fault tolerance, where you can achieve this criteria, but you need to have redundant qubits. So the redundancy in terms of extra number of qubits or extra number of gates you need, I wrote only in terms of qubits, will be polylogarithmic in n. So if I take the ratio of the number of qubits and gates that you need in the presence of noise divided by the number that I need if there is no noise, that would be polylogarithmic in n. So it will grow as n grows. But still, that was a very good result because at least we could achieve this. Maybe the redundancy is high, but recently there has been work in 2014 and also in 2018 where it has been shown that you can achieve constant redundancy. So this, instead of polylogarithmic, this would be O1. Okay. But all these results are applicable when noise is below a threshold, like sufficiently small, not too high. But again, this is not the goal of this talk. We want to understand the other way around, the converse. What is the converse? We want to get a lower bound on redundancy. What is the minimum redundancy? Because these papers achieve constant redundancy. We want to understand what is the minimum constant. And also we want to understand what is the noise beyond which we cannot achieve this goal at all. If the noise is more than, say, for example, in the depolarizing noise, the P was my noise parameter. I want to get a result. If P is more than something, then I can never achieve this goal. So this is converse. And there have been some work, very classical work and very fundamental work. So I'll list some of them, and all of them focus on this thing. They try to figure out what is the noise threshold, like beyond which no reliable quantum computation is possible. That means we cannot achieve that goal in the previous stage. Okay, so that means whenever we can achieve this goal, we say reliable quantum computation is possible. When we cannot, we say reliable quantum computation is not possible. So these papers try to look at the noise beyond which reliable quantum computation is not possible. So there are some work. So I focus on this work. They are all only work. So this threshold is for P, this particular P. So first one was 0.74, then 0.5, then 0.29, then 0.33. So this looks like not an improvement, but in fact it's a very great improvement because all this work only worked for depolarizing, but this work was considering a general noise. And what they show that this threshold has a connection to quantum capacity of a quantum channel. So this Qn is called quantum capacity, which simply means the number of qubits that can be reliably transmitted over n channel use. So here the n is channel use, not the input size in our circuit. It's the channel use. And so this is very similar to classical capacity, as similar. And they show that whenever it's 0, you cannot do quantum computation, and that gives you a threshold. Because what happens for depolarizing, this Qn becomes 0 for P beyond 1/3. And that's why they get 0.33. So, and this also applies to other noise also. But more importantly, this Fauzi et al. Paper in 2022 also gives a lower bound on redundancy. For example, all these papers only said if noise is above this threshold, then you cannot do reliably. But they don't say that if noise is below the threshold and I can do reliably, how much redundancy do I need? None of this paper give that answer. But this is the first paper to give that answer. So our approach is also very similar. We get a lower bound on redundancy and also get a noise threshold. So this came in 2020, January or February, and we saw it in April. And by that time, we have started working on our problem, our approach. And when we first saw the result, we thought, oh, they have already done what you wanted to do. But then later, while reading the paper in detail, and we realized there are a lot of difference with what we do. So the main thing I would say that if you notice the previous bounds were gate size dependent, depends on this G. Okay, and you get 0.5 when you put G equal to 2. Okay, but this result does not have any G.
Sorry, Avhishek, can you remember what is G exactly?
Oh, G, sorry, yeah, G was the number of inputs to a quantum gate and number of outputs of the gate. Okay, yeah, sorry about that. So G was the number of input to the quantum gate and the output, and this threshold is dependent on G. But this paper 2022, they got a bound which works for all noise, but they did not have G there. So what we got, it has a gate size dependence, and what we got, see, all these results are for asymptotic results. When number of input qubits are going to infinity, we get a non-asymptotic bound. And not only that, our bound extend to non-i.i.d noise, some special kind of non-i.i.d noise which are of practical importance. Our bound extends to that. And there is some another dissimilarity, which is this work assumes there is something called perfect decoder and perfect decoder at the end, which we do not assume. So there are these differences, but in spirit they're very similar in sense, because they also connect this problem to a capacity, quantum capacity problem. Okay, and I love this paper. This is very, and actually when I saw the paper after our results, my writing got influenced because I wanted to compare with, put in the same framework. So this is a very nice paper, you should read, but there are many differences with our work, as I said. So let me go to the bound in our case. So the bound I'll give on redundancy. Redundancy, remember, number of physical qubits that you need divided by number of logical qubits that you are computing with. And that bound, so for us, this is the main bound, and where n is the number of input qubit. Okay, and this is a non-asymptotic bound. It applies for any n. Okay, it's applicable for any n. I think the only condition you need, n has to be greater than or equal to 2g. That's all. As long as n is greater than or equal to 2g, it applies for any n. But interestingly, if you want to compare with their bound, which is asymptotic, we can see we have to take n to infinity. In that case, we get the redundancy lower bound to be this, where this quantity IC is something called coherent information of the channel. Okay. So what is coherent information? Coherent information is, so look at this quantity, sorry. So look at this quantity. So this S of n g rho g. So this n g rho g is the output after noise, after rho g goes through noise, and this S is the entropy. Just like Shannon entropy, in quantum there is von Neumann entropy, and one can show that Shannon entropy is a special case of von Neumann entropy. And this S rho g and n g rho g, this is a joint entropy of the input and the output. So this is marginal entropy minus joint entropy, which is actually negative conditional entropy. So in classical, hxy minus hy is conditional entropy. Here it's the opposite. It's like hy minus hxy. So this is negative conditional entropy. But funny thing in quantum is that because of something called entanglement, for certain states, certain choices of rho g, this negative conditional entropy can be positive, which is never true in classical. In classical, negative conditional entropy is always positive, and hence negative conditional entropy is always negative. But this is not the case here, and it can be positive for certain states. So when you maximize over all choices of rho g, you get a positive quantity, and this is called the coherent information of this channel, and the bound in is in terms of this. Now, how do we compare this with the existing bound? The interesting thing, what we can directly claim, that this bound is actually better than 1 by qn that was done in the 2022 paper, simply because this 1 by qn, which is the quantum capacity, is known to satisfy this equation. Okay. I won't get into why, but this is known to satisfy this infimum over all k. But for us, this is just g, so definitely this is better than this infimum. And what is known, that this bound is actually strict, like strict for depolarizing noise. Okay, it's and the bound is quite non-trivial for g less than or equal to 5. Okay, so the gap is non-trivial. So that sense, our lower bound on redundancy is non-asymptotic, and the asymptotic version is tighter than the existing results. Not only that, from this bound you can get, using some more work, you can get a noise threshold also. So what it turns out, that the noise threshold in the previous work was corresponding to qn equal to 0, solving that. And what happens, that whenever qn is 0, is known from this in relation that this IC will also be 0. And whenever IC is 0, that's actually our noise threshold, because that means G by IC is infinity. That means that lower bound on redundancy is infinity. So which means you cannot do computation. So that's the noise threshold, because, and that's also tighter. Okay. And not only that, our bound, this particular bound or this bound itself extends to non-i.i.d noise. It does not have to be i.i.d. On all the previous results, i.i.d is necessary. In our case, it's not needed. So only thing that within a gate, remember out after a gate, there was this noise, and the noise was working i.i.d on each bits. If that's not true, it's not i.i.d, but some general noise, still our result goes through. Okay. And same result, only thing you have to do, instead of this n tensor product G, we have to replace that by this quantity, ng. And here also, instead of n tensor product G, you have to replace by ng. And everywhere. Then we'll get the bound. So it's an easy extension from i.i.d case to non-i.i.d case in our model. But here the noise can be correlated in a gate, but across gates, it should be independent. And that's actually a reasonable assumption, because the correlation generally happens at a gate because you're operating on those qubits together. But across gates, they are physically separated and they should be uncorrelated. Okay. So the last thing I want to mention is in this result, that our result extends to non-unitary computation, which may not be of that practical interest, but we could extend it mathematically, so we did it. But it may not be of that practical interest. Okay. So said that, so this is the result, but what is the implication, practical implication? Okay. First, it's always good to know the limit on redundancy and noise threshold. And we have understood the limit better because we have improved the bounds. Nobody knows the exact limit, but we are improving the bounds in the right direction. So that's very good. But another thing I want to mention, so there is something called noisy intermediate scale quantum circuits. So current circuits are called noisy intermediate scale quantum circuits because they are intermediate scale, in the sense they can operate with 50 or 50 to 100 qubits, which are not really large. So that's why intermediate scale, and they're also very noisy. And all the previous bounds work for n going to infinity. So n has to be at least 10,000 or million or something. But our bound works for any n, and hence is applicable to the current niche circuits also. And that has another practical benefit, is that this bound can help some kind of first order planning for experimentalists. I'm not telling that this will totally guide the experimentalist in the right point, but it will kind of guide them in the ballpark direction. So for example, let's consider two technologies. We have, say, two particular quantum technologies. Let's say one is ion trapped and one is superconducting qubit. Name for two technologies. We call it technology A, technology B. One technology gives me a certain gate size, say 5, but its noise, the depolarizing noise P is say 0.2. Another technology gives me a gate size G equal to 3, but its noise is little less, maybe it's 0.15. Now, how do we compare which technology is better? So one way to compare them is which one requires less redundancy to do something correctly. And that will get from our bound, and then one can compare the technologies and say maybe the one is better than the other. That one use of our bound. Another is, as I was attending a conference 2 weeks back where many experimental physicists were talking about, and they're discussing how to form certain gates, how to do certain operations like C0, which are important operations. And in certain technologies, this correlation across qubits was quite common. It was not uncommon. So one may want to understand what kind of correlation is bad and what kind of correlation is good. And by evaluating this quantity, which we saw in previous page, actually we'll understand for whichever correlation this quantity is more, that correlation is good. For whichever technology because of the correlation this quantity is less, that technology is bad, because 1 by this, G by this is our redundancy. So redundancy requirement will be more in the technology where this quantity will be small. So that way you can also compare which kind of correlations are good or which kind of correlations are bad. Okay. So, okay, so Dr. Noiri, how much time do we have?
I think you have a few minutes now if you want to
Okay,
also
so then I'll wrap up. I have this proof approach, which may be of interest to some of you, but I'll skip it in the interest of time. So the idea is what you do, it, as I said, we boil down this quantum computation, finite qubit quantum computation to finite block length quantum computation. In particular, multiple interdependent finite block length quantum system. And that's how we got the bound. And then we invoke finite block length quantum information theory. But yeah, I won't get into that. I'll just conclude saying what we saw here is we presented some kind of a tighter bounds on redundancy and noise threshold using finite block length quantum communication, but I did not get into this connection so much. So our bound is gate size dependent and also applies to all noise. So it kind of takes good from both sides of the literature, gate size dependent and applicable to all noise. It's also has a finite bound, so finite qubit bound, so applicable to intermediate scale computing. And as I said, some of these bounds can help experimentalists in planning. And also it extends to correlated noise at a gate and hence can be useful for certain systems where I heard in an experimental talk, there is something called non-Markovian noise. Previously, people believed the noise is always Markovian in physical systems, but it turns out there are non-Markovian noise. And in those cases, this our bound for correlated noise will be useful. Okay. So with that, I want to thank you all for your attention. And again, thanks for the invitation. And I'll be very happy to take any questions you may have.
Thank you. Any question in the room? Yeah, François.
Thank you, Avhishek, for the nice lecture. I have just questions coming from information theory viewpoint. So you alluded to this sort of erasure channel, right? Where you keep the signal or lose it by. But are there other type of noises which are of interest, say additive noise? Does it make sense to add a matrix which is trace zero or something like that? Or
I think there is something called an additive noise, but I'm not too sure what is that. There is, I think, something this bosonic photon communication. There is some noise like that, and that's actually in fiber optics. You can see something like that noise. I forgot what is exactly called because I never worked on that area, but I think there is. And there are other noise models also, like there is an erasure noise model, which is just erasure version in the quantum world. Then there is something called unital noise, which is interesting, which is almost like classical noise. So unital noises or Pauli noise, they're also called Pauli channels. I would say they're just the classical counterpart, a counterpart of a transition probability matrix in the quantum world. And many of the properties of the classical noise extend there. For example, there is something called this Holevo additivity of classical capacity and Holevo capacity versus Shannon capacity. So they all match for this channel because these channels are almost like classical. But additive, I think I've seen somewhere, but I'm not too sure. This Dr. Noiri can comment on this. I think he will be more knowledgeable in photonic because that's generally seen in fiber optics. And
yeah, I had the second question also. I mean, so you alluded lots of to lots of information theoretic concepts, but I didn't see. Perhaps I missed it. I mean, the notion of code book or so.
Yes, so those are all hidden. So that's a very good point. So those are in the proof approach, which I did not talk about.
And tell us about the code books. How do they look like? I mean, what is
so that's a good point. As I'm doing Converse, I don't have to come up with a code book. So I just have to say no code book can do it.
Right.
So, but the achievability part for even finite block length, and there are code books. There are interesting code books even for finite block length. So they're just like classical also. So they have to map the message into a code book and then send it. So all these ideas of a code book, then ensemble of code books, they are still here in quantum world, but they're all hidden under the proof. And again, as it's Converse, I don't have to talk about them.
Yeah.
I just have to say there cannot be a code book through some randomization argument. But yes, code books are always there. Definitely they are there.
Does
They're all
random
hidden.
coding play a role in some arguments?
Yes. So, for example, again, this is Converse, so we don't go through random coding arguments. But for example, when I somebody talk about capacity of a quantum channel, there are two kind of capacity: classical capacity and quantum capacity. In the classical capacity, again, the randomization argument is there. Similar to Shannon, there is a notion of typicality in quantum, just like typical sequence. There is a notion of typical quantum sequence in quantum also. So there are one-to-one mapping certain concepts. Only certain things keep changing. For example, this conditional entropy can be negative here, and it's often negative. On the other end, in classical, conditional entropy is always positive. So this is because of one very funny thing that happens in the quantum world is, in classical world, joint entropy is always more than marginal entropy. That's always true. In quantum world, joint entropy can be zero, while marginal entropy is the most random entropy. That's something called this Bell pair or Bell state, for which the Nobel Prize was given this year. So that's a very, I would say, non-classical behavior, and there is no way of simulating it classically. So there is something called this hidden local variable theory, which is a classical theory which cannot explain it. So the only explanation is this von Neumann framework. So that's something different.
Are there some questions online?
Okay, sure, please, yes.
No question online. Other question in the room? So I have a last question. So if I understood well, so you find better bounds. Do you think that one can improve these bounds to have even better bounds in the future, or what do you think about that?
Yes. So if you see the kind of bound, say the noise threshold that you need for achieving something is much smaller than the converse. Still, there is a lot of gap. There is a chance to improve it. I think it can be improved, but that's more. I know intuitively how to improve, but the idea is, so now what we're looking at one layer of computation and giving a bound, but you have to see how the errors accumulate across layer and how to add those errors to give a converse. That's where I think something can be done, but as of now, I don't have a concrete way of doing it. But I think it can be improved. It can be improved. So in the bound, as of now, the depth of the network does not show up. So I believe a bound can be done where the depth should also show up. For example, Fauzi's paper that had a bound dependent on depth, but that depth required to be exponential in number of inputs. But I think something can be said for smaller depth also, but that would be the approach to get a tighter bound, in my opinion. But as of now, I don't know a kind of a rigorous way of getting there.
Okay. Thanks again.
Okay, thank you. Thank you again for the opportunity, and thanks for the interactions and the questions. Okay, thank you.